welcome to the session. Is it screen is visible?
Yes, sir.
Yes. A continuation of a network theory. In the yesterday's session, in the previous session, I discussed some models of questions with respect to resonance. Then remaining models that I want to complete. Then we'll start the next concepts with respect to network theory, that is the coupled circuits. That is also very important topic for GATE or ESC or any competitive point of view. Yes, friends. In the previous session, all these models of questions that I already covered with respect to resonance, this is completed, all this. The next one is continuation of that, the next model of question. For the circuit shown in figure, here circuit is missing. I'm drawing this one. This is the given circuit. Come on, students, do this. This 10 kilo ohms, 5 millihenry, 5 microfarad. The supply is this is given 60 cos omega t. For the circuit shown in figure, what is the voltage across capacitor at resonance condition? Yes. This concept I already explained in detail. What is the voltage across the capacitor formula also that I discussed in detail at resonance condition. Then how to solve this one, students? Come on, do this. The voltage across the capacitor equal to, here not only magnitude, angle is also asked. That's why I'm writing, we know that I naught into, let the current at resonance, I naught is the current at resonance condition. We know that at resonance condition, current is maximum. I naught into minus jXC. Okay. Shall I write like this? I naught into XC at angle of minus 90 degrees. Then option B is not the answer, option D is not the answer. Either A or C is the answer. Okay. Now we want to find I naught and XC. I naught and XC. Yes, but frequency is not given here. That's why we want to find the frequency also. Shall I write like this? I naught by omega c. Xc is 1 by omega c at angle of minus 90. Here omega is the frequency at resonance condition. Or if you have any doubt, you can write omega naught into c. Any notation you follow, you can write omega naught also, no problem. Okay, whatever the notation you convenient, that notation you follow. Is I naught by omega c at angle of minus 90 degrees. Then at resonance condition, current is maximum. What is I naught, students? That is 60 by 10 kilo ohms. 10 kilo ohms is 10 into 10 cube. That is 6 milliamperes. Now, capacitance you know, but I want to find the omega. Then at resonance, what is omega? 1 by root LC. 1 by root LC. What is L? 5 millihenry. 5 into 10 power minus 3. What is C? 5 into 10 power minus 6. We do this calculation. How much we are getting the omega? Yes. This 5 into 5, 25. 25 root is 5. That is 1 by 5. This is 10 power minus 9. Yes, it's 5 millihenry, 5 microfarad. How much you get, friends? You do this calculation approximately how much you are getting. This is not 5 millihenry. Please correct this. It is a 50 millihenry. That is 50 millihenry. Then we can get like this. This is 50 millihenry that I am substituting. Please correct that. This is 50 millihenry. Okay, that I'm substituting 50 into 10 power minus 3. This is 0, 10 power minus 2. 10 power minus 2 means 10 power minus 8. Then you can get 10 power 4. Okay. 1 by 5 is 0.2. 0.2 into 10 power 4. That is 2 into 10 cube. That is radians per second. Omega is radians per second. 2 into 10 cube rad or 2 kilo radians per second. 2 kilo radians per second. Then I know the omega also. Now you find what is the voltage across the capacitor. What is I naught? You got 6 milliampere. 6 into 10 power minus 3. What is omega? 2 into 10 cube. What the capacitance? 5 microfarad. 5 into 10 power minus 6. Do this calculation, students. What you are getting? The 10 cube, 10 power minus 6, 10 power minus 3. This is cancelled. Then 6 by 10. That is how much? 0.6. 0.6. But at angle of minus 90 degrees is there already. 0.6 at angle of minus 90 degree volts. Then which option is correct? Option C is correct. Understood? Any doubt?
Yes.
Yes. Simple model, but you won't remember the formulas. A series RLC circuit has a resonant frequency of 50 radians per second and a quality factor of 80. If the impedance at resonance is 10 ohms, then the values of R, L, and C is given by. Come on, do this. You want to find the resistance value, inductance value, and capacitance value. And resonant frequency is given, quality factor is given. And resistance, impedance at resonance is 10 ohms. Impedance at resonance is 10 ohms. We know that you can easily find the resistance value because at resonance, what is the condition? At resonance, Z equal to R. Z equal to R. Impedance already given. Impedance is how much it is given? 10 ohms. That's why R equal to 10 ohms. We got the resistance value easily. R equal to 10 ohms. Because it is a impedance is given, but you want to find the resistance. But at resonance, impedance equal to resistance. That is R equal to 10 ohms. Okay. Then we want to find the inductance. For that, quality factor is given. How much quality factor it is given, students? Quality factor equal to omega naught into L by R. Quality factor equal to omega naught into L by R. Yes. How much quality factor it is given? 80. Resonating frequency, omega naught directly it is given, 50 radians per second. Inductance, resistance just now you calculated, 10. Then how much inductance you can get? Yes, come on, do this. 800 by 50, 16 Henry. Is it correct? We can get the L equal to 16 Henry. Okay. We know the resistance, we know the inductance. Resistance is 10 ohms, inductance is 16 Henry. A is not the answer, D is not the answer. Either B or C is the answer. Now you want to find the capacitance. Then how to find the capacitance, students? One method to find the capacitance is we can use Q equal to, we can also write in terms of capacitance quality factor, you can also write 1 by omega naught CR. Okay, you can also write the quality factor formula like this. Q is how much? 80. Omega naught is how much? 50. Then C into resistance is how much? 10. Then from this, how much C you can calculate? Yeah, 25 microfarad. This is one method to solve the capacitance value. Or we can also use the formula omega naught equal to 1 by root LC formula. Clear? Yes, friends. Omega naught, 50. L value you calculated. Then you calculate the C. That is also another method. We can use this formula or we can use quality factor formula. Then you can calculate the resistance, inductance and capacitance. Then option B is correct. Next. A series RLC circuit has a bandwidth of 20 radians per second and resonant frequency of 1 kiloradians per second. If resistance is 10 ohms, then what are the values of inductance, capacitance respectively? All these are at resonance condition only. Yes, a series RLC circuit has bandwidth of 20 radians per second and resonant frequency of 1 kiloradians per second. If resistance equal to 10 ohms, then you find the inductance and capacitance values respectively. What is the solution? Bandwidth. In series RLC circuit, in series, yes friends, RLC circuit, tell me what is the bandwidth, what is the formula for bandwidth, is equal to, yes friends, R by L. Bandwidth, all these concepts are already given students. You please go through previous lectures. R by L, that is how much it is given? 20. Bandwidth equal to 20. Okay. Then resistance value is given, then you can calculate the inductance. Then inductance equal to R by 20. Resistance is how much? 10. This is 20. How much? This is 0.5 Henry. We are getting the inductance is 0.5 Henry. Okay. Then how to calculate the capacitance? Simple. Because bandwidth is 20 radians per second it is given. Bandwidth is 20 radians per second it is given. Yes. Then you want to calculate the capacitance. Yes. And frequency is also given, resonating frequency. Then what the formula for omega naught equal to 1 by root LC? Simple. This is how much? 1 kiloradians per second. 1 into 10 cube equal to 1 by root L into C. I'm making the square on both sides. Instead of this one, directly I'm writing omega naught square formula. Omega naught square equal to 1 by LC. Omega naught is how much? That is 1 kiloradians per second. 1 into 10 cube whole square is equal to, yes friends, 1 by L is 0.5 into C. Then what the C equal to? 1 by 0.5 is 2 into 2 by 10 power 6. That is 2 microfarad. That is L is 0.5 Henry, C is 2 microfarad. L equal to 0.5 Henry, C is 2 microfarad. Which option is correct? Option D is correct. That means you want to remember this formula, simple formula, bandwidth equal to R by L formula. Friends, in network theory point of view, we can easily answer the questions from two-port networks, coupled circuits, resonance. This is, we can easily answer the questions even in AC analysis also. Even AC analysis also you can easily answer the questions. But if you want to answer the questions on fundamentals, if you want to answer the questions on transients, okay, that more practice is required. But remaining topics are, even in three-phase circuits also we can easily answer the questions. Yes. Can anybody try this question? The resonating frequency of the network shown given, not above network, of the network is given by, what is the resonating frequency in this circuit? That means you want to find the frequency at resonance condition in this circuit. Yes. I told already one general condition. If you want to find the resonating frequency for any given circuit, if it is a series circuit, write down the impedance formula, equate the imaginary term equal to 0, we can get the condition at resonance. From that, we can calculate the resonant frequency. If any parallel circuit is given, write down the formula for admittance, then equate imaginary term equal to 0, then we can get the frequency at the resonance condition. That is the method we follow. If it is a series circuit, write down the impedance formula. If it is a parallel circuit, write down the admittance formula. Yes, friends. Here we want to find the what is the frequency at resonance condition. Omega naught formula that you want to find. Yes. I want to write the formula for admittance. For that, what I am doing here first, see, you can write like this. Let here voltage is V1 means what the voltage here also, it is also V1. Here also V1. Yes, friends, here also V1. Then let the current is in the circuit is I1. Then I1 equal to, how we can write? Apply the nodal analysis, V1 by R plus V1 by J omega L plus V1 minus KV1. V1 minus KV1 by whatever the capacitance you can write minus JXC. Minus JXC. Is it correct? That I am writing. Yes, friends. Then I1 by V1 equal to 1 by R. 1 by R. V1, I am making the V1 is common. V1 is common. 1 by R plus 1 by J omega L. 1 by J omega L. 1 minus K by, I am writing this minus JXC is 1 by J omega C. This is XL. XL is, actually it is XL. That XL I am writing as a omega L. J omega L. XC I am writing. That XC is I am writing 1 by omega C. But this minus J I am bringing into the denominator 1 by J. Clear, friends? That is 1 minus K by 1 by J omega C. Then shall I write like this? Therefore, I1 by V1 equal to 1 by R plus 1 by R plus this J I am bringing into numerator minus J by omega L, minus J by omega L. Next, this 1 by J omega C is goes to the numerator, J omega C into plus J omega C into 1 minus K. What is I1 by V1, students? This is the admittance. 1 by R minus J by omega L plus J into omega C into J omega C into 1 minus K. Now at resonance condition, to get the condition for resonance or at resonance, which term you can equate to 0? At resonance, which term you can equate to 0, students? The imaginary term equal to 0. You can equate the imaginary term equal to 0. Then minus 1 by omega naught. Resonance means replacing omega by omega naught. Minus 1 by omega naught into L plus omega naught into C into 1 minus K equal to 0. Important for 2 marks. Then from this 1 by omega naught into L is equal to omega naught into C into 1 minus K. Then omega naught square equal to 1 by LC into 1 minus K. Then what is omega naught, students? Then omega naught equal to 1 by square root of LC into 1 minus K. Is it clear? Omega naught equal to 1 by square root of LC into 1 minus K. Then which option is correct? Omega naught equal to 1 by square root of LC into 1 minus K. Option D is correct. That is the result. Not only this circuit, sir. If any circuit is given, then if it is a series circuit, better to calculate the impedance and equate the imaginary term equal to 0. If it is a parallel circuit, you calculate the admittance and equate the imaginary term equal to 0. Then we can get the condition for resonance, and we can get the resonating frequency expression. Any doubt?
Understood, sir.
Yes, thank you. Yes, students. The next one. Students, once again, all triple and EC students. See, once you are preparing for gate point of view means, you don't feel like this. Most of my seniors are not, even though they are prepared, they are not getting the good ranks like that. You don't feel like that. Sir, once you are preparing for gate means not only for gate point of view, you are getting the subject knowledge. Once we can get the subject knowledge, not only for gate point of view, for other, so many other opportunities also there. For example, mainly nowadays, triple and EC students, you have the good opportunities in VLSI and embedded systems also. Then after completing your BTech, then you can do the either 4 months or minimum 6 months of course. Then we can get the good package also. I seen so many my students also this year selected for nearly 6 or 7 students are selected by taking the VLSI. Just 6 months course after BTech. In Bangalore, they taken the coaching for 6 months course, and the package is yearly package, starting package is 17 lakhs. Understand? That means you want to build up your subject. Sir, then what is the need of these subjects in VLSI, sir? And compulsory, every subject is important. Once you are doing the technical course means every subject knowledge is very important. If you want to face any interviews, then subject knowledge are very important. That is my suggestion. See, once we are preparing for coaching means, once we are preparing for gate means not only for gate. This is useful for your career, total your career also. The subject is useful. But nowadays, two opportunities. Three opportunities. One opportunity is you go for the gate for MTech in IITs, then your life will settle, either IIT or minimum NIT. Then another opportunity, softwares. So much opportunities are there. That is the second opportunity. The third opportunity is after completing your BTech, then you go for either VLSI or embedded. That is very important. The future is always maximum VLSI and embedded only, maximum. That's why for EC and triple students, it's a good opportunity. These three opportunities are there. But for triple students, one more opportunities, go for the government, state government jobs. Central government jobs means compulsory PSUs, compulsory gate exam. Like that, so many opportunities are there. You can utilize that opportunities. If you want to utilize that opportunities, first, you must be perfect in your aptitude and reasoning skills and mathematical skills and also the subject skills. Then you can succeed in any competitive exam. Yes, friends, a parallel RLC circuit resonates at a frequency 5 kiloradians per second and has an admittance of 0.25 millisiemens at resonance. If C equal to microfarad, then values of R and L are. Students, come on, do this. It is a question based on parallel RLC circuit. A parallel RLC circuit resonance at a frequency 5 kiloradians per second and has admittance of 0.25 millisiemens at resonance. If C equal to 2 microfarad, then the values of R and L is. It is also simple. We know that in parallel RLC, At resonance, what are the conditions, friends? At resonance, what are the condition? Y
Y is equal to 1 by R.
Yeah, very good. Y equal G, that is Y equal to 1 by R. Very good. Use this relation. Admittance already given. Admittance is how much it is given? 0.25 into 10 power minus 3. This is equal to 1 by R. Then you find the resistance. How much resistance we can get? 4 kilo
Yes, sir.
ohms. Is it correct? Yes. R equal to 4 kilo ohms we are getting. Over. Then you want to find the L. To find the L, you know the even in parallel RLC circuit also, what is omega naught formula? 1 by root LC. Formula is same in series and parallel. Only tank circuit formula will changes. Then omega naught is how much it is given? 5 kilo radians per second. 5 into 10 cube. 1 by root L. You want to find the inductance. C value already given 2 microfarad. Then from this you find the L value. Better to write on square on both sides. Directly you can get the L. Come on, how much L you got? Respond.
Twenty millihenry, sir.
Yes, 20 millihenry. Then option B is correct. So one more question. A parallel RLC circuit has bandwidth 100 radians per second and the lower half power frequency, that is a cutoff frequency, lower cutoff frequency, 1000 radians per second. If R equal to 200 ohms, then the values of L and C are respectively. Yes, friends. A parallel RLC circuit has bandwidth. That means here we want to know the formula of what is the bandwidth in parallel RLC circuit. Yes. What is the bandwidth in parallel RLC circuit? In parallel RLC circuit. All these formulas in detail that I already explained, students. In parallel RLC circuit. Come on. Bandwidth equal to 1 by RC. How much bandwidth it is given? The bandwidth is 100 radians per second. 100. That is in terms of omega it is given. Omega 2 minus omega 1. 100 radians per second means is not F2 minus F1. It is 100 hertz means F2 minus F1. It is 100 radians per second means omega 2 minus omega 1. Yes, resistance is given. We can easily calculate the capacitance. Then capacitance equal to 1 by R into 100. Then 1 by R is how much? 200. 200 into 100. Then how much capacitance we can get, students? Approximately, it is a 50 microfarad. To simplify that one, we are getting the 50 microfarad. Then C equal to 50 microfarads. We got the C equal to 50 microfarad. Okay. Then which option 50 microfarad is there? Either B or D. A is not the answer and C is not the answer. Then which one you want to find? L value. Then how to find the L value? Yes. Formula for to find the L is omega naught equal to 1 by root LC. Omega naught equal to 1 by root LC. But you don't know omega naught. Okay. Then how we can solve this? Yes, students. Yeah. What is the bandwidth formula? Bandwidth equal to omega 2 minus omega 1. Omega 2 minus omega 1. Bandwidth is how much it is given? 100. Omega 2 into lower cutoff frequency is how much? 1000. Then how much omega 2 we can get? 1100 radians per second. Yes, 1100 radians per second. Now you know this one, students. Omega naught equal to square root of omega 1 into omega 2. Just like f naught equal to square root of f1 into f2. This derivation also I given. Omega naught equal to square root of omega 1 into omega 2. Then square on both sides. Omega naught square equal to omega 1 into omega 2. What is omega naught square? 1 by LC is equal to omega 1 is how much? 100. Omega 2 is how much? Sorry, omega 1 is how much, friends? 1000. It is the 1000. Yes. Omega 2 is how much? 1100. Then you want to find which one here? Inductance. Then C equal to L equal to 1 by C into 1000 into 1100. Already C value you know. Then you find the what is the L value.
$18.2 millihenry, sir.
Very good. 18.2 millihenry. That is the correct. Then which option is correct? Option D is correct. 18.2 milli. See, all these are most of the questions with respect to resonances, formula based questions only. Even you seen yesterday I explained 2 questions which that is asked in GATE 2022. That's also direct formula based questions. Yes, this is a simple question. In a parallel RLC circuit shown in figure at resonance, I explained the concept in detail. We know that at resonance, the total current is passing through which one? At resonance, the total current is passing through which one? At resonance, the total current is passing through resistor. And what about the L and C elements? At resonance condition, the parallel combination of L and C elements acts as a open circuit or short circuit. There is no current through the L and C elements. That is, it acts as a open circuit. I given this point also. Acts as an open circuit means there is no current. There is no current through L and C. Because the total current is passing through a resistor means what the current through L and C? There is no current. There is no current means it acts as an open circuit. Then which option is correct? Current I flow through the resistor. A is correct. Total current is flowing through the LC combination. Wrong. Current in inductor and capacitor is 0. C is also correct. The total current flowing through L and C combination. Yeah, sorry. This is current in inductor and capacitor is 0. The total current flowing through LC combination is 0. That is correct. The total current flowing through the LC combination is 0. Then both A and B is the correct. Both A and B is the correct. The sum of the currents flowing through the L and C combination is 0. That is the meaning. For this proof also I given students, please go through the concept. Next. In parallel RLC circuit, if the value of capacitance C is increased, remaining all other elements values are same, then which of the following quantity also increases? In parallel RLC circuit, if the value of capacitance C is increased, if the value of capacitance C is increased, remaining all other element values are same, then which of the quantities also increases? Which quantity will increases? Yeah. First we will see. Yeah. Omega naught equal to 1 by root LC. If the capacitance is increases, what the resonating frequency decreases. That means resonating frequency is not increases. That's why option A is not the answer. Okay. What the bandwidth formula? Bandwidth equal to 1 by RC. Bandwidth equal to 1 by RC, students. Bandwidth equal to 1 by RC. If the capacitance is increases, what the bandwidth decreases. That means bandwidth also not increases. That is option C is also wrong. Clear? Next, what the quality factor formula? Quality factor equal to omega naught into CR. Quality factor equal to omega naught into CR. Is it clear? Omega naught into CR. We can also write like this: omega naught is 1 by root LC into CR. Then we can also write like this. What you can write, students? R into square root of C by L. Then if the capacitance is increases, If the capacitance is increases, what about the quality factor? Increases. I'm talking about parallel RLC circuit, sir. In the previous problem, you told Q equal to 1 by omega naught CR, sir. But why you are writing omega? That is a series RLC. It is a parallel RLC. Exactly reverse. Okay. Then if C is increases, which quantity is increases, students? Only quality factor is increases. If C is increases, only which factor is which parameter is increases? Only quality factor is increases. Keeping other parameters are remain same. For the circuit shown in figure, what is the resonating frequency? It's very simple. In this circuit, you want to find the what is the resonating frequency. What is the formula for resonating frequency, students? Omega naught equal to 1 by root LC. It's very simple. L, you know, L is how much? 100 microhenry. Then C you want to find. This C and C is parallel. What is the resultant? 1200 picofarads. Parallel combination of capacitors directly added. Exactly opposite to resistance concept. 1200 picofarads. This 1200 in parallel with which one? 600. Sorry, series. In series with the 600. 1200 in series with 600. If 1200 is in series with 600, this is 1200. Then what is the C equivalent? 1200 into series combination, capacitor series combination, students. 1200 plus 600. How much you can get? 1200 into 600 by 1200 plus 600. That is 1800. This is 600 in 3. 3 times it goes. Then 1200 by 3, 400. The C equivalent equal to 400 picofarads. Now you substitute here 1 by square root of L into L is how much? 100 microhenry. 100 into 10 power minus 6. C is how much? 400 picofarads. Pico in the sense 10 power minus 12. Now tell the students how many mega radians per second we can get. How many mega radians per second? Come on, do this.
Five, sir.
Yes, it is equal to 5 mega radians per second we can get. That is the answer. Next. A series RLC circuit resonates at a frequency of 8 kHz. The nature of the circuit impedance at a frequency of 3 kHz would be. Come on, it's very simple question. Respond. A series RLC, given a series RLC circuit.
Resistive, sir.
See, at resonance condition, it is a resistive. At what frequency it is resonance? 8 kHz. It is a resonance at 8 kHz. That means at 8 kHz, no doubt at all, it is a resistive. But the nature of the circuit impedance at frequency 3 kHz. At 3 kHz, what is the nature of the circuit element? You know this already given for series resonance. This curve I given. Yes, friends. This is F naught equal to how much it is given? 8 kHz. This is 3 kHz means this F naught, whatever the F is given, F is 3 kHz. This 3 kHz is F is less than F naught. No? F is less than F naught. But you know this, for less than resonating frequency, what is the condition, you know? Xc greater than XL. Which is more dominant? Capacitive. Here XL is greater than Xc. Inductive more dominant. This concept I already explained in detail. Then this frequency 3 kHz is less than the resonating frequency. 3 kHz is less than the resonating frequency means it at which side it come? Capacitive side or inductive side? This is Xc greater than XL means which is more dominant? Capacitive more dominant. This is inductive is more dominant. Then what is the nature of the element? Nature of the circuit. Which is more dominant? Capacitive. That's why which option is correct, friends? Option A is correct. Because given frequency is less than the resonating frequency. In a series RLC circuit, for low frequency, capacitive is more dominant. For higher frequency, inductive is more dominant. That is the meaning. That means for 3 kHz frequency, in this circuit, current lags the voltage or current leads the voltage? In this question, for 3 kHz frequency, current lags the voltage or current leads the voltage? Capacitive, what about the current? Lagging or leading? Current is leads the voltage. Current leads the voltage. Yes, friends. Then last question. Next one more question is also there that I want to explain. For the RLC network shown below, the impedance seen at terminal AB is circuit is missing. That circuit I am drawing. This is the given circuit. Okay, this is a different question. This model still now it is not framed, but you can expect. This is 1 Henry. This is 250 millifarad. And this is 4 ohms. This is given. For the RLC network shown below, the impedance seen at terminal AB is Z. This is terminal AB. Yes. Now L and C are changed such that new values of impedances becomes Z nu equal to 10 power 4 into Z. The new values of RLC are given by. Here Z nu equal 10 power 4 Z means this is called magnitude scaling. Z nu equal to, yes, we are increasing the impedance by 10 power 4. Yes, it is called magnitude scaling. Yes, friends, it is called, yes, magnitude scaling. Magnitude scaling. In a magnitude scaling, there is no change of the frequency response. That is, frequency response remains unchanged. Frequency response remains unchanged. That is, frequency response remains unchanged. Then the values of elements will be changes. Then how much value it is changing? Then scale factor, how to calculate the scale factor? This concept I'm not given because that is not there in your syllabus, but I'm explaining the one question. Then scaling factor equal to, yes friends, Z nu by Z. This equal to 10 power 4. Then what is the new value of resistance? The new value of resistance equal to Km. That scaling factor, let us assume that Km. That is Km into R. That is 10 power 4 into how much actual resistance? This is how much? It is 4 ohms. That is how much we are getting? 40 kilo ohms. What is the L nu? L nu equal to Km into L. Scaling factor into L. Then how much you can get? 10 power 4 into 1. That is 10 kilo Henry. What is the C value? C nu equal to C by Km. C by Km. This 25 microfarads we can get. This model not framed in any competitive exam, but remember this model also. Then which option is correct, friends? 40 kilo ohms, 10 kilo Henry. Another one is 25 microfarad. This about different models of question. Then last model of question that I am explaining here. Please concentrate. The network below acts as, this is the question asked in GATE exam. The network, previous GATE question, this one. Whatever the previous up to now, what are the models I given? That models also previous models, not the same questions, previous model. With that knowledge, you can solve the previous gate questions. The network below, students, below acts as dash filter. It acts as a dash filter. Here, this is the given network. This is the R1, and this is L and C elements. And this is R2. Values are not given. Without giving the values, then we want to identify this is acts as a which filter. This is plus minus Vi. This is V0. The circuit acts as a which filter. Then how to analyze this type of circuits means, take the three frequency students. One lower cutoff frequency, or you can take the low frequency, that means zero frequency ideally. High frequency, that is infinity frequency ideally. Then you take the resonate frequency. Tell me at omega equal to 0. If omega equal to 0, then what about this LC combination? At omega equal to 0, students, this LC combination acts as a short circuit. That LC combination acts as a short circuit. Sorry. At omega equal to 0, which acts as a short circuit? Inductor or capacitor? Not total LC combination. Inductor or capacitor? At omega equal to 0, which acts as a short circuit? Come on. Inductor or capacitor?
Inductive.
Inductor. Because XL equal 2 pi FL now. F is 0. XC equal to 1 by 2 pi FC now. 1 by 2 pi FC. Frequency 0, or you can write XL equal to omega L. Because I taken omega. Omega L. XC equal to 1 by omega. Omega equal to 0 means capacitor acts as a XC infinity. It is an open circuit. Okay, this is the equivalent. This is Vi, this is V0. Then how much V0 you can get? Apply the voltage divider rule. What is V0 you can get, students? Then Vi into R2 by R1 plus R2. Voltage divider rule. Then what is V0 by Vi? The magnitude of V0 by Vi is equal to R2 by R1 plus R2 we are getting. This is somewhat constant value. This is the constant value. That means at low frequency, we can get the constant frequency characteristics. The output characteristics are the constant. Then at omega equal to infinity. At omega equal to infinity. Omega equal to infinity means then which is the open circuit, which is the short circuit? At omega equal to infinity, then inductor is open circuit. Then which is the short circuit? Capacitor is short circuit. Is it correct? Okay, this is the R2. Okay, this is Vi, this is the V0. Then what is V0, students? Remains same. Vi into R2 by R1 plus R2. Then what is V0 by Vi? V0 by Vi equal to R2 by R1 plus R2. Understand or not? Okay, this is constant. At high frequency is also constant characteristics. But at omega equal to omega naught. At omega equal to omega naught means 1 by root LC. Now tell me, at omega equal to omega naught, at resonance condition, LC circuit acts as an open circuit or short circuit? Just now I explained. LC circuit acts as a open circuit or short circuit. There is no current through which one? At resonance condition, there is no current through which one, sir?
Combination of LC.
L and C element. That's why it acts as an open circuit. Once it acts as an open circuit, what is V0?
Vi.
What is V0?
Vi, sir.
How it is Vi? It is the open circuit. It is not the open circuit. See, if it is like this, then it is open circuit. Then your answer is V naught equal to, in this case, V naught equal to Vi. But here it is a open circuit. Here the resistance. The total voltage will appear here only. This Vi will appear here only. But what is V naught? There is no current through this resistance, sir. Because it's open circuit now. There is no current through this resistance. What is V naught? What is V naught? 0. What is V naught? 0. Then if you draw the frequency characteristics, if you draw the frequency response characteristics with respect to omega, now see, at low frequencies, we are getting the constant characteristics. At resonate frequency, it is a 0. Again, at higher frequencies, we are getting the constant characteristics. This is the frequency characteristics we are getting. This is which filter, friends? This is which filter? This is the band of frequency. It is the band of frequency. That band of frequency is allowed or stop. This band of frequency becomes 0. At resonate frequency, that is output is 0. At resonate frequency, output is 0 means it is allowing the band of signals or stop the band of signals. It stops the band of signals. It stops the band of signal means it is which filter characteristics? Come on.
Band reject.
Band reject or band stop. Very good. It's a band stop or band reject filter. That is the answer. That's why what is this filter? Band stop filter. This is the previous gate question. Like this we can analyze. Clear? This is about the different models of questions with respect to resonance. With this, total resonance concepts are completed. The next chapter I am going to start in coupled circuits, or that is the magnetic circuits. This is there in syllabus, in GATE syllabus, even for ESC syllabus also this concept is there. I am discussing the coupled circuit means indirectly I am discussing the magnetic circuits concept. Magnetic circuits or magnetic circuits concept. First you will see some introduction, students. Later on we go for in detail about coupled circuit, what is the coefficient of coupling, what is the series aiding, series opposing, parallel aiding and parallel opposing. Then with respect to transformer, what is the concept of coupled, that is in coefficient of coupling and mutual inductance, all this that I want to explain. I think you know this is the minimum knowledge. If the charges are at rest, if any charge is at rest, produces only electric field or only magnetic field or both electric field and magnetic field. Can anybody? If the charges are at rest, that means if the charge is not moving, the charge is at rest, then it produces only electric field or only magnetic field or both electric field and magnetic field. Yes, sir. This is minimum fundamental. If the charges are at rest, if the charges are at rest, produces only electric field. Produces only electric field. Is it correct? Then this is called which one? This is called electrostatics concept. Electrostatic concept. You studied the electrostatics. That all of you well known about these concepts in even in EMF. If the charges are at rest, produces only electric field, that is called electrostatics. Charges in motion. Charges in motion. That means if any current is passing through the conductor like that, charges are in motion. That is current. Charges in motion means, charge in motion means what it is called? Charge is flowing means, then which is produced? Current. That is, current produces both electric and magnetic field. Both electric and magnetic field. Electric and magnetic field. We know that this minimum fundamental point, if any conductor carries the current, around the conductor magnetic field is produced. If the conductor carrying the current means automatically electric field is present. Then if that conductor carries the current, means current is flowing through the conductor. It is not stationary. Charge is not stationary here. Current is flowing through the conductor. If current is flowing through the conductor, around the conductor magnetic field is produced. Sir, how, sir? That that is done by the one experiment also, Eirsted experiment. That is given by the Eirsted experiment. According to Eirsted experiment, that is given. That is, magnetic field is produced. That magnetic field is represented by imaginary lines. Those imaginary lines are nothing but a flux lines. Yes, sir. This is the conductor. This is the conductor. It is a straight conductor. If any conductor carries the current, this conductor carries the current, then around the conductor a magnetic field is produced. A magnetic field is produced. That magnetic field is produced by imaginary lines. Those imaginary lines are nothing but a flux lines. Those imaginary lines are nothing but a flux lines. That is the magnetic field. Sir, what is the flux means? This is the flux. Magnetic field itself is the flux only. Yes. I'm talking about the straight conductor. Now this also produces the flux. Then how to find the direction of this flux, students? Come on. How to find the direction of this flux? If any conductor carries the current, around the conductor magnetic field is produced. That magnetic field is represented by imaginary lines. Those imaginary lines are nothing but a flux lines. Then how to find the direction of this flux? Yes, the direction of flux is determined by using right hand thumb rule or screw rule. Is it correct? The direction of flux is determined by using right hand thumb rule or screw rule. Is it correct or not? Yes.
Yes, sir.
Now tell me, then how to apply the right hand thumb rule or screw rule? Yes, friends. See how to apply the right hand thumb rule or screw rule. I think all of you know this one. If it is a straight conductor, thumb indicate the current direction. These curled fingers indicate the flux direction. Clear? If it is a straight conductor, thumb indicate the current direction. The curled fingers indicate the flux direction. Now tell me, in this conductor, what is the direction of the flux? Clockwise or anti-clockwise? What is the direction of the flux? Clockwise or anti-clockwise? Thumb indicate the current direction, and this is the direction of the flux. Clockwise or anti-clockwise? In the first conductor.
Anti-clockwise.
Anti-clockwise. Okay, this is the direction of the flux. This is that is, flux is in which direction? The flux is oriented in which direction? The flux is oriented in the anti-clockwise direction. Next, you see this one. This is the direction of the current. Then what is the direction of the flux? What is the direction of the flux? Clockwise direction. The direction of the flux is clockwise direction. The direction of the flux is clockwise direction. Okay, this like this we can apply the flux direction is clockwise. This is according to right hand thumb rule. According to right hand thumb rule. That is, if any conductor carries the current, around the conductor magnetic field is produced. That magnetic field is represented by imaginary lines. Those imaginary lines are nothing but a flux lines. Those imaginary lines are nothing but a flux lines. Now see the students, for example, in general, it is a straight conductor. If you take the solenoid conductor, or solenoid coil, actually it is a coil. This is the current direction. Now if it is a solenoid coil, here also we can apply the right hand thumb rule. But in this case, curled fingers indicate the current direction. Thumb indicate the flux direction. Exactly opposite. Curled fingers indicate the current direction. Thumb indicate the flux direction. Then what is the direction of the flux? Left to right or right to left? Okay, this is the direction of the flux. This is thumb indicate the flux direction, but curled fingers indicate the current direction. Okay, this is the direction of the flux. The flux lines are moving like this. Like this we can apply. That means the direction of flux is determined by using the right hand thumb rule. Generally, there is two types of magnets, students. One is permanent magnet. There is two types of magnets. One is permanent magnet. Another one is electromagnet. One is permanent magnet. Another one is electromagnet. Yes. One is permanent magnet, another one is electromagnet. Now tell me, these permanent magnets are, this minimum knowledge is required. Hard magnetic materials or soft magnetic material? The permanent magnets are hard magnetic materials or soft magnetic materials? It is a hard magnetic materials. Hard magnetic materials. Yes. What about this one? It is a soft magnetic materials. Soft magnetic materials. Yes. What is the example of hard magnetic material? It is made with alnico material. Aluminum, nickel, cobalt. And the soft magnetic materials are made with soft iron. It is made with soft iron. These permanent magnets are having high retentivity. The permanent magnets are having high retentivity. What about these magnets are having low retentivity? Low retentivity. Because of high retentivity, these magnets are having high residual flux. High residual flux. Because of retentivity property only we can get the residual flux. This is less residual flux. These magnets are having less residual flux. Okay, these are minimum differences between the hard permanent magnets. Generally, permanent magnets means this is the permanent magnets. Okay, this is a representation of permanent magnet. For example, it is a north pole, it is a south pole. Electromagnets means just like a whatever I told, solenoid coil. Its coil is nothing but electromagnet. For example, this is the core, iron core. On this core we are placing the winding. This is which one? Electromagnet. This is the electromagnet. In the case of permanent magnet, always the flux lines are moving from which one, students? The flux lines are moving from which one? North to externally. The flux lines are moving from which one? North to south. Generally, the flux lines are start from north. Then internally it is a south to north. Okay, this is the permanent magnet, and this is which one? Electromagnet. This is the electromagnet. Yes. Now see the students, very important observation here. For example, this is one electromagnet. This is one electromagnet. This is the electromagnet. This is the coil. The current is given like this. This is the direction of the current. This is a coil. The orientation of direction of current is like this. Let this is X, this is the direction of the current. Let this is the X and this is the Y. Then tell me, X acts as a which pole? Y acts as a which pole? Can anybody respond? X acts as a which pole and Y acts as a which pole?
X north pole and Y south pole.
Very good. Apply the right hand thumb rule. If you apply the right hand thumb rule, curled fingers indicate the current direction. Curled fingers indicate the current direction. Take the right hand, sir. Take the right hand. Curled fingers indicate the current direction. Thumb indicate the flux direction. That means the flux lines are moving like this. This is the direction of the flux. That means the flux lines are moving like this means the flux lines are moving this. Means flux lines are starting like this. Then it acts as from where the flux is started, north. That's why it is a north. Then it is a automatically it is a south pole. That's why X acts as a north pole, Y acts as a south pole. For example, one more example I am giving. This the minimum fundamentals are required to understand the total concepts. This also one more coil. Yes, electromagnet. The winding is placed like this. Now this is the direction of the current. This goes to the back side, again it comes to the front side. Back end of the coil. This current is enter into back end of the coil, again front side. Again this goes to back end, again it coming to the front end. Like this. Let this is the X and this is the Y. Then X acts as a which pole? Y acts as a which pole? Again apply the right hand thumb rule. Curled fingers indicate the current direction. See the current direction, students. Curled fingers indicate the current direction. Yes. Okay, this one. The curled fingers indicate the current direction. This one. And thumb indicate the which one? flux direction. Thumb indicate the flux direction. Now, then which is the north pole and which is the south pole? The flux direction is like this. This is the direction of the flux. That means flux lines are starting like this. Clear? Then this is the north pole, this is the south pole. Then X is which pole? South pole. Y is which pole? North pole. Always the flux lines are starts from north pole. The flux lines are starts from north pole. Yes. Yes. For example, one more example. Let this is the coil. And the direction of current is like this. Let this is X is the one coil. The direction of current is like this. Then now you tell me X is a which pole? X. I'm not giving dot and cross. It is a X. Don't feel like this. It is a dot and cross. This is the X. Okay. And this is the Y. And the direction of current is like this. Y and X is which poles? X is which pole and Y is which pole?
X south pole, Y north pole, sir.
Yes. See, apply the again right hand thumb rule. If it is a curved nature is there, if it is a coil or curved nature is there, if it is a coil or curved nature is there, then which one? Yes, friends, if it is a curved nature is there, see the direction of current. Apply the right hand thumb rule. Again, apply the right hand thumb rule. Apply the right hand thumb rule. See, the direction of current is this one. This is the direction of the current. And this indicates, curled fingers indicate the current direction, means thumb indicate the flux direction. That means flux is entering or leaving. Students, understand or not? This is the direction of the current. Then this is thumb indicate the flux direction. That is flux is entering or leaving. Entering. Means at which pole flux is enter? At which pole flux is enter? Come on. South pole or north pole? At which pole flux is enter, sir? South pole. Understand or not? Then see the next conductor. This is the direction of the current. This is the direction of the current. Understand? And the flux is leaving. Flux is leaving. From which pole flux is leaving?
North pole.
North pole. Clear? Okay, this is the south pole and this is the north pole. For example, one more example I am giving. Okay, let this is the coil. And this conductor is given like this. This is a conductor representation. This winding. Winding is represented like this. And let this magnet is X magnet. This X is dash pole. And the winding is represent. This is the dot. At this winding dot. This is a dot means automatically it is a cross. Now X is which pole? This is the one magnet, student. This is one magnet. Then X is which pole? At this winding, what is the X? North pole or south pole? Very good, north pole. See, this is the dot. This is the dot. Dot means current is leaving. Current is leaving. Away from that one. Away from that. This one. This is the direction. See this one. Cross means like this. Current is entering into the conductor. Current is entering into the conductor. Current is entering into the conductor. Dot means current is moving away. Then this is the direction. If this is the direction of current means, then this is the direction of the flux. Then flux lines are leaving from this one or entering from this one? Entering into this one. Flux lines are leaving. Flux lines are leaving means leaves from which pole? The flux leaves from which pole?
North pole.
North. Like this, you can answer the fundamental questions. You can. Then what is this pole? Is what this indicates? Is the north pole or south pole? If you want to answer, this is a minimum fundamental is required. Yes, friends. Now with this knowledge, then before starting the in detail about what the flux, what is the MMF, and what is the mutual inductance, all this. First, I want to explain analogy between electric and magnetic circuit. Electric and magnetic circuit. Electric and magnetic circuit. This minimum knowledge, fundamentals already you know this one. Yes. In one side you can write electric circuit. In another side you write magnetic circuits. Yes. Generally in electric circuit, the source is we can define as either EMF or voltage. We can define as a EMF or voltage. EMF or voltage. What about in magnetic circuit? What are the equivalent in magnetic circuit? We can define which one? This EMF or voltage is in volts. What about in magnetic circuit, students? Corresponding to that, what you can define in magnetic circuit? MMF. MMF, magnetomotive force. What is the MMF? Number of turns into current. What are the units of MMF? What is your answer? What are the units of MMF? Ampere turns. Ampere turns. Next. In electric circuit, we can define the current. We can define the current. That is I in amperes. This is in amperes. But similarly in magnetic circuit, which parameter you define? Analogous to this, which parameter we can define in the magnetic circuit? Here current is flowing, but in magnetic circuit, which is flowing? Flux is flowing. The flux is flowing. That is flux. What are the units of flux? Weber. Next. In the case of electric circuit, there is a concept of resistance to oppose the flow of current. That is a resistance. Resistance. What is the definite? How to define resistance? Voltage by current. Voltage by current. Then the units is resistance in ohms. But here what you can define? Corresponding to resistance, what the analogous here? Reluctance. You can define the reluctance. The reluctance, we can use any symbol. Here I am using the S symbol. The reluctance, it's just like voltage by current means here MMF by flux. MMF by flux. Voltage by current is the resistance. Voltage is equivalent to MMF. Flux is equivalent. Current is equivalent to flux. MMF by flux. mmf by flux. That is the reluctance equal to Ni by pi. Ni by pi. The reluctance equal to Ni by pi. What are the units, students? What are the units? Ampere tons per Weber. Ampere tons per Weber. Because mmf units is ampere tons. Flux units is Webers. Ampere tons per Weber. Next. In the case of electrical circuit, R is defined as rho L by A. R equal to rho L by A. Is it correct? Or it is also equal to L by rho is I am writing 1 by sigma. Rho is the resistivity. 1 by sigma is the conductivity. Rho equal to 1 by sigma A. L by sigma A. Then what about equivalent in the case of magnetic circuit? That is the reluctance. Resistance is L by sigma A, but reluctance is L by mu A. Here the electric circuit is the conductivity concept. But what about here? Permeability concept. Understand or not? In electric circuit, this is the conductivity concept. But in magnetic circuit, this is a permeability concept. That's why L by mu A. L by mu A. You can also write like this, L by mu naught into mu R into A. What is the mu naught, students? Where mu naught is the absolute permeability, that is the permeability of the free space. What is the permeability of the free space? Come on, what is the permeability of the free space? 4 pi into 10 to the power of minus 7 Henry per meter. 4 pi into 10 to the power of minus 7 Henry per meter. Clear, students? This is the analogy between the electric circuit and the magnetic circuit. One more, the fifth one. In electric circuit, we can define the electric field. What is the definition of electric field? The electric field equal to, in electric circuit, we can define the electric field volts V by D. That is volts per meter. The electric field unit is volt per meter. Then what about in magnetic circuit? What you can define? This electric field, here magnetic field intensity. H you can define. That is the magnetic field intensity. Then mmf by L. mmf per unit length. Per unit length. That is Ni by L. Ni by L. Then what are the units of magnetic field intensity? Ampere tons per meter. Ampere tons per meter. Then one more parameter. Here we can define the current to density. Current to density. In electric circuits, we can define the current to density. What is the current density? J equal to I by A. What are the units, students? Ampere per meter square. But here, which parameter we can define? Flux density. We can define the flux density. Yes, come on. The flux density B equal to pi by A. Is correct? Yes, friends. What are the units of flux density? What is the units of flux density? Weber per meter square. 1 Weber per meter square equal to which one? 1 Tesla. 1 Weber per meter square equal to 1 Tesla. 1 Tesla. Okay. Next, one more parameter we can define. In the case of electric field, we can write the current density and conductivity J equal to sigma E. This at starting in the fundamentals that I given, this is the first form of Ohm's law. Is correct or not? J equal to sigma E. Then in this case, here J is B. Is it correct? J equal to B. Sigma equal to J equal to B in the sense I am talking about analogy. This is J, it's similar to B here. Sigma is similar to mu here. E is similar to H here. B equal to mu H. E is H, similar, analogous. J is B. Sigma is mu. B equal to mu H. B equal to mu H. Yes. In the case of electric circuit, the series resistance, in series resistance, R1, the equivalent of series resistance is R1 plus R2 and so on. Even in the case of magnetic field, the series reluctance equal to S1 plus S2 and so on. If the magnetic circuits are connected in series, the resultant reluctance. Then what about the parallel? 1 by Rp in parallel combination, 1 by R1 plus 1 by R2 plus and so on. Even in the case of magnetic circuits also, even in the magnetic circuits also, in a parallel circuit, the resultant reluctance equal to 1 by S1 plus 1 by S2 and so on. Same concept. Where the resistance, here the which one? It is a reluctance. Here it is a reluctance. Clear, friends? This is the analogy between electric field and magnetic field. Now, no time giving. We know that what is the flux equal to? The flux equal to MMF by reluctance. What the flux equal to, students? What is the flux that you know? If any conductor carries the current around the conductor, magnetic field is produced. That magnetic field is represented by imaginary lines. Those imaginary lines are nothing but a flux lines. Now I am asking one question that you know in EMF subject. Here I told that if any conductor carries the current around the conductor, magnetic field is produced. Direction is determined by which one? Right hand thumb rule or screw rule. What about the magnitude, sir? Magnitude is determined by which rule? The magnitude of magnetic field is determined by which rule? Can anybody respond? The magnitude of magnetic field is determined by which rule? Yes. The magnitude is determined by, we can use Biot-Savart's law or you can use the Ampere-Circuitor law. We can use Biot-Savart's law or Ampere-Circuitor's law. In detail about that you see in your EMF subset. Biot-Savart's, that point also remember. The magnitude of the magnetic field is determined by Biot-Savart's law or Ampere-Circuitor law. You can apply any rule. But if it is a very complex to determine the magnitude, then only you go for the Ampere-Circuitor law. Generally, we are using the Biot-Savart's law. But in complex circuits, it is very difficult to determine using the Biot-Savart's law. That's why we can go for the which one? Ampere-Circuitor law. This is a magnetic field concept. But in the case of electric field concept, how to determine the magnitude of electric field? The magnitude of electric field is determined by using which law? The magnitude of electric field is determined by using which laws? We can use, here in electric field also there is a two laws are there. One is Gauss law, another one is Coulomb's law. One is Gauss law, another one is Coulomb. That means in electric field we are using the Gauss law and Coulomb's law, but in magnetic field we are using the Ampere-Circuitor law and Biot-Savart's law. That two differences also you remember, students. Now, what the flux pi equal to? MMF by reluctance. Flux pi equal to MMF by reluctance. This is the fundamental formula that you know. Flux pi equal to MMF by reluctance. The MMF equal to N into I. Reluctance I am giving the notation is S. S is the notation that I am giving. Yes, that means flux equal to Ni by S. Flux equal to Ni by S. But for a particular circuit, magnetic circuit, once you can design any coil, what about N? N is constant. N is constant. What is the reluctance for same magnetic circuit? S is also constant for same magnetic circuit. For same magnetic circuit. For same magnetic circuit, S is also constant. Then if N is constant, S is constant, always the flux is proportional to current. That's the reason. If any conductor carries the current, around the flux is produced. This neglect the saturation effect. I'm not considering any saturation effect. If saturation effect is neglected, always the flux versus current characteristics are always which one? It is a linear characteristics. The flux versus current characteristics are linear characteristics. Okay, this is the minimum fundamental, students. Now, with this knowledge, I'm going to discuss in detail about what the self-inductance, what the mutual inductance, what is the series aiding, what is the series opposing, then what is the energy stored in the series circuit, what is the energy stored in the parallel circuit, then what the coefficient of coupling, then what is the equivalent representation of ideal transformer as a coupled circuit, all these concepts that I want to discuss. In the next class, I will continue, students. This is the fundamentals only today. Yes, friends, any doubt?
No, sir.
Is it okay? All are following?
Yes, sir.
Okay.
Yes. Okay, thank you. I'm ending the session.